Hello student, I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I am going to discuss Group 14 elements, the carbon family. Last class I have discussed about chemical properties of Group 13 elements and their compounds. Also I have discussed usage of boron and aluminum and their compounds. Now I am going to discuss group 14 elements, also called the carbon family. Carbon, silicon, germanium, tin and lead are the members of group 14. Carbon, that is a C, silicon Si, germanium Ge, tin Sn and lead Pb are the member of group 14. Group 14. Carbon is the 17th most abundant element by mass in the earth crust. It is widely distributed in nature in free as well as in the combined state. In elemental state, it is available as coal, graphite and diamond. However, in combined state, it is present as metal carbonate, hydrocarbons and carbon dioxide gas. Carbon dioxide gas is present, that is 0.03% in air. One can emphatically say that carbon is the most versatile element in the world. Its combination with other elements such as hydrogen, oxygen gas I am talking about, hydrogen gas, oxygen gas, chlorine and sulfur provides an astonishing array of materials ranging from living tissues to drugs and plastics. Organic chemistry is devoted to carbon containing compounds. A special chemistry is there, organic chemistry, that is chemistry of carbon compounds or chemistry of carbon containing compounds. It is an essential constituent of all living organisms. Naturally occurring carbon contains two stable isotopes, C12 and C13. There are total three isotopes, then C12 and C13, and one more is there, that is the C14. In addition to C12 and C13, third isotope C14 is also present. It is radioactive isotope with half-life period 5770 years. 5770 years half-life period, and is used for radiocarbon dating. Means this is used to find out how many years old any tree is there or any wood, old wood, if it is there, then how old this wood is there, then that can be known by the use of this C14. Silicon, now I am discussing about the silicon. Silicon is the second, that is 27.7% by mass, most abundant element. Second most abundant element. First is oxygen. Silicon is the second most abundant element, 27.7% by mass on the earth's crust, and is present in nature in the form of silica and silicate. Silicon is very important component of ceramics, glass and cement. In all three things, silicon is found. Now come to the germanium. Germanium exists only in traces, very less. And about the tin, tin occurs mainly as a cassiterite ores, as a cassiterite. That is also called SNO2. And what about the lead? Lead is that its ore is galena, PbS. It exists in the form of lead. Okay, lead sulfide. Galena is PbS, lead sulfide. Then lead exists as a lead sulfide. Now you can say other you should know about the germanium. Ultra pure form of germanium and silicon are used to make transistor and semiconductor device. This is very important. Ultra pure form of germanium, GE. Okay, this is the semiconductor. Ultra pure form of germanium and silicon both are semiconductors, and it is used to make transistor, or you can tell it is used in transistor and semiconductors devices. The important atomic and physical properties of the group 14 elements. Now I am going to discuss. Okay. Then first I will discuss atomic number. Atomic number of carbon is 6 and silicon is 14. Silicon, Si. Okay. Its atomic number is 14. Germanium, Ge, its atomic number is 32. Always remember, 32 is germanium, Ge, because it is used as a semiconductor in transistor. Even in computer also it is used, germanium and silicon. Then germanium atomic number is 32 and tin is 50. Sn, tin is also called Sn, stannous. And lead, Pb, lead is Pb, its atomic number is 82. Then I told about the atomic number. Now I am going to tell about the atomic mass, gram per mole. Okay. Now already I told you just up to atomic number 20, mass number is roughly double of atomic number. Then for carbon, atomic mass is 12.01, and silicon, that is the 28. 14 is the this atomic number, and mass number is 28.09. And for germanium atomic mass is 72.60. And tin, that is the stannous, its atomic mass is 118.7. And lead is 207.2. This I have told about the atomic mass. Okay, gram per mole, it is in gram per mole. Now electronic configuration. For carbon has a 6 atomic number, 6. Then first is the helium structure, helium electronic configuration, and after that 2s square, 2p2. Helium, you know, that is the 1s square. Okay. Then this first you should write electronic configuration of inert gases, and then you write last orbit you write. Then in the case of carbon, I am telling you helium. First you write inert gas configuration and then you write 2s square 2p2. Now silicon. Silicon is 14, atomic number 14. Then it has neon configuration and after that 3s square 3p6. Always new orbit will open. Keep in mind. For each element, new orbit will be opened, and if it is incomplete, if a previous orbit is incomplete, then that also will be written. You know how to fill the electronic configuration by following above rule. Then now germanium, GE32, atomic number 32. Then this argon electronic configuration you write, and after that 3D10, it was empty, it was not filled, that's why you are writing 3D10. Now new orbit is 4s square 4p2. Always 2 S2 and P2 will be there, S square and P square, means S2 and P2 in all elements. For this 14th group, always new orbit will be opened and lasting will be S2 and P2. Only orbit number will change, and incomplete D or F orbital will be also written. Then now germanium 32, then you write this argon electronic configuration, and after that 3D was vacant, then now it will fill here. Then 3D10 4s square 4p2. Like that way, tin, stannous SN 50, it is a krypton electronic configuration, and after that you write 4D10 5s square 5p2. Okay, 5 square 5s2 and 5p2. And last lead PB 82. Then here GNN electronic configuration you should write, and then here 4F14, it was not present in the last orbit. Now here you have to fill it, and then 5 also you have to fill it because 5 was also not there in previous. Okay, then you know that for that 3D will be filled, then 4 3D, then 4D, then 4F. When all will be filled, then it will go to the next orbit, that you know. Then like that way, what was not filled in previous, now it will filled in the next. You can say element. Then tin I told you, krypton, and after that 4D10 and 5s square 4D10 5s square 5p2, and last lead, that is the xenon 4F14 5D will start, and 6 square and 6p square. Okay, xenon electronic configuration. After that 4F14. Okay, this you have to fill it, and after that 4 is filled, then 5D is just, it will start, it is 0, and after that 6s square 6p2. This I have told you about the electronic configuration. Now covalent radius, there is a considerable increase in covalent radius from carbon to silicon. Thereafter, from silicon to lead to silicon to PB, a small increase in radius is observed. This is why this is happening. Then this is due to the presence of complete filled D and F orbitals in heavier members, and its value I am telling you. covalent radius in picometer. Then carbon has 77 picometer. 1 picometer, already I told you, 10 to the power minus 12 centimeter. That is called 1 picometer. Okay, 10 to the power minus 12 meter, not centimeter. Okay, then this is a picometer. Then carbon has 77 picometer, and silicon is increasing 118, and after that germanium, its covalent radius is also increasing 122, and tin is 140, continuously increasing, and lead 146 picometer. Okay, now ionic radius, you can see ionic radius, already told you variation is there. Carbon, for carbon, it is till date it is in confusion, leave it. Silicon is 40. Ionic radius means M4 plus, it is in two form, M4 plus or M2 plus. Then first I am telling about the M4 plus, okay, in picometer, ionic radius, okay, radius of an ion. Then for silicon 40 picometer. Now for germanium 53, and tin that is 69, and lead 78. Okay, then here it is increasing. Now in case of M2 plus, ionic radius in the form of M2 plus. Okay, actually oxidation number is 4 also and 2 also, plus 2 and plus 4 oxidation state. Then plus 4 I told you now, told you that it for silicon it is 40, for germanium 53, tin 69, and lead 78. But ionic radius in case of M2 plus, then now for carbon and silicon it is not available, but germanium it is 73, and tin is 118, and lead is 119. Actually some things will be controversy, that things data will be not given, and what are the main these things reason for all the things, then this D orbitals and F orbitals in heavier metals, already it will be filled. Then due to that some you can say confusion will be there, and some discrepancy will be there, it will be not very clear. Now I am telling about the ionization energy. Then here 4 type of ionization energy is possible, because oxidation state is up to 4, plus 2 is also there, plus 4 is also there, means maximum 4 electron can be removed. Okay, but always you keep in mind, electrons which are closer to the nucleus, it is very difficult to remove, and there they require more energy, and which electron which can be easily removed, they require less energy. Okay, only on this concept all 4 ionization energy is written, only on this concept. Then first I am telling in case of carbon, okay, and ionization enthalpy or energy, whatever you can tell, that is in kilojoule per mole. Then in case of carbon, first ionization energy, that is the delta H, F you can say for the formation. Ionization, that is 1086, first ionization energy, and second obviously it should be more, because they are closer to nucleus, then it is 2352. Third one is again should be more, then it is 4620, 4620, and fourth, then again furthermore 6220. See, it is increasing. Okay, it is increasing. Now, like that way, silicon, see, first ionization energy is 786, second is more 1577, third is 3228, fourth one is 4354. But here it is remarkable, carbon has a more ionization energy, carbon, but silicon is all four are less than carbon, because size is increasing. Third case you can see, again this is less than this silicon, and silicon is less than carbon. Then I am telling about the germanium, Ge. Now it is the first ionization energy is 761, second is 1537, third is 3300, and fourth is 4409. Okay, then this is the less than silicon, but in each cases, first one is less, second one is more, third one is furthermore, and fourth one is highest. Now in case of tin again it is less than germanium. Then 708, first ionization, second is 1411, 15 is 2942, and fourth one is 3929. It is less than, these are the less than germanium. Okay, but in tin it is everywhere it is down, fourth one is highest and first one is least. Now lead again you can see it is again less than stainless, all are less than previous. Then lead is less than tin. Then now it start with 715, and then first one is 715, second is 1450, third one is 3081, fourth one is 4082. Okay, then these are the less than tin, but here also first one is less and last one is more. Now come to the electronegativity. Electronegativity meaning earlier understanding, it wants to attract or it attracts the electron. Then here electronegativity you can see carbon, its value is highest in the you can say group, in 14 group it is the highest 2.5, and this silicon and germanium both are this silicon, germanium, tin, all three have same value 1.8, all three. Fourth one is again you can say same, only little more, 0.1 more, means 1.9. Then this carbon has more tendency to attract the electron in comparison to silicon, germanium, tin and lead. Okay, silicon, germanium, tin, they have value, electronegative value same. Fourth one is also roughly same but little more, 1.9. Now heaviness, density, gram per cc, gram per centimeter cube. Density, heaviness we can tell, means mass of 1 cc. What is the this thing, volume is 1 cc. Then what is the, you can say, mass of 1 cc? That is called density. Density is equal to mass by volume. Then volume is same in all cases. Then what is the mass? That is telling about the heaviness. Then for carbon you can see it is heavy in, it is you can say in all, not in all, comparative is there. Density of carbon is 3.51 for carbon, and silicon is less. Silicon is little lighter, 2.34 gram per cc, and carbon was 3.5 gram per cc. And germanium was heavy, or germanium is heavy, you can tell, 5.32, and tin is further heavy, 7.26 gram per cc, and lead is heaviest in the group, that is 11.34 cc. Okay, melting point. Then melting point is very high for carbon, 4373 Kelvin. After that, second is the silicon, 1693, and third is germanium, 1218, means it is decreasing, and tin is 505, but in case of lead it is little more, 100 more, 600. Tin is 505 and lead is 600. And boiling point of carbon is not known exactly, but silicon is known 3550 melting point in Kelvin, 3550, and germanium is less, 3123, and tin is further less, 2896 Kelvin, and list is 2024, that is for lead. This I have told you about the boiling point. And electrical resistivity means resistance. Electrical resistivity, this is related to resistance. Then its value is for carbon, that is between 10 to the power 14 to 10 to the power 16 ohm centimeter at 293 Kelvin. 10 to the power 14 to 10 to the power 16 ohm centimeter at 293 Kelvin. And silicon, that is very less, 50. Germanium is also 50, and this very less for tin and lead. Tin is 10 to the power minus 5, 10 to the power minus 5, very less, and lead is 2 into 10 to the power minus 5. Then this I have discussed about the atomic and physical properties of group 14 elements, and little more I want to tell you about these properties. That physical, I am talking about the more about the ionization enthalpy. The first ionization enthalpy of group 14 member is higher than the corresponding members of group 13. In comparison to 13, 14 has a higher. Why? Because of a small size. The influence of inner core electrons is visible here also. In general, the ionization enthalpy decreases down the group. A small decrease in delta H from silicon to germanium, germanium to stainless, and slight increase in delta H from stainless to lead. Already value I told you. And why this is happening, slight increase? This is due to the poor shielding effect of intervening D and F orbitals, and increase in size of the atoms. In the group, always size will increase, and in period it will decrease. Okay. Now other things about the electronegativity. Due to a small size, the elements of this group are slightly more electronegative than group 13 in comparison to 13. Here it is more. Due to a small size, the elements of this group are slightly more electronegative than group 13 elements. The electronegativity values for elements from silicon to lead are almost the same. Already I have told you. Now other things I am telling you, all group 14 members are solid. Okay, all group 14 members are solid. Carbon and silicon are non-metal. Listen here. Carbon and silicon are non-metals. Germanium is a metalloid. Metalloids means it will have character of metal and non-metal. Metal and non-metal. And this will also show semiconductor property. Means 50% roughly it will conduct electricity. Then all metalloids will show semiconductor properties also. Then silicon and germanium always think it is metalloid and are semiconductor. Tin and lead are soft metals. In this group, last two, tin and lead are soft metals with low melting points. Melting points and boiling points of group 14 elements are much higher than those of corresponding elements of group 13. Okay, this I have told in comparison with group 13 elements. Now I am going to discuss chemical properties of group 14 elements. Oxidation state and trends in chemical reactivity. I am going to tell oxidation states and trends in chemical reactivity. The group 14 elements have 4 electrons in the outermost shell. You have seen in electronic configuration. Okay, 4 was common, and somewhere you have seen that D and F was also there. Okay, this you keep in mind. Hence 4 is common. The group 14 elements have 4 electrons in outermost shell. The common oxidation states exhibited by these elements are +4 and +2. Carbon also exhibits negative oxidation state, +4 as well as -4 also, plus and minus both. Carbon also exhibits negative oxidation state. Since the sum of the first 4 ionization enthalpies is very high, compound in +4 oxidation states are generally covalent in nature, because it is very difficult to release the electron. Okay, compounds in +4 oxidation states are generally covalent in nature. Why? Since the sum of the first 4 ionization enthalpies is very high. Okay, that's why compounds in +4 oxidation states are generally covalent in nature, because fully they can't give, hence only displacement will be there. Then you have seen that there is a sharing. Covalent bond means sharing, they will not give full, but in ionic it will give complete transfer of electron, but in covalent no complete transfer, only sharing, displacement of electrons is possible. That's why it is covalent. carbon compounds are covalent in nature. In heavier members, the tendency to show +2 oxidation state increases in a sequence, like germanium is less than stannous, stannous is less than lead. Okay. In heavier members, the tendency to show +2 oxidation state increases in the sequence, like germanium is less than stannous, stannous is less than lead, means lead you have more tendency to show the +2 oxidation state. Question is asked. It is due to the inability. Why it is happening? It is due to the inability of n square electrons of valence shell to participate in bonding. Okay. It is due to the inability of ns square. Ns square, they will not take part. Ns square and np2 is there in the last. Then np2, that p will take the electron, they will take part in the bond formation. But ns is before np, then they require more energy, hence it will show inability. That is also we can tell inert pair. In heavy metals, they will not take part. P will take part because it is outside. ns square np2, this p will take, p electron will take part in the bond formation. But s is inner, little inner, and they will show inability to take part in the bond formation. That's why this is also called inert pair, this ns square, that is called inert pair. This I told you the reason. It is due to the inability of ns square electrons of valence shell to participate in bonding. That's why +2 is common. And as you will go down, then lead will have little more tendency to show +2. This question is asked, that's why I have told about more. I told more about this. The relative stability of these two oxidation state vary down the group. Carbon and silicon mostly show +4 oxidation state. Both carbon and silicon mostly show +4 oxidation state. What about germanium? Germanium forms stable compounds in +4 state and few compounds in +2. Germanium generally will form +4 and less. There also few compounds are there. There it will be in a +2 state. Tin forms compounds in both oxidation state, +2 and +4 also. Tin, that is the SN. SN in +2 state is a reducing agent. Keep in mind, in +2 state, reducing agent means it will donate the electron. It can give the electron. Lead compounds in +2 states are stable. Lead in +2 state is stable, and in +4 state are a strong oxidizing agent. Lead I am talking you, +2 is stable, and in +4 state are a strong oxidizing agent, means it can take the electron. Oxidizing agent, it can take the electron. Okay. In a tetravalent state, means +4, in tetravalent state, the number of electrons around the central atom in a molecule, like carbon in CCl4, C is in the middle and 4Cl is there, then maximum electron is 2 into 4, 18 electron. Carbon in CCl4, that is it is a 8 electron. Correct. In tetra valent state, the number of electrons around the central atom in a molecule is 8. Being electron precise molecules, they are normally not expected to act as electron acceptor. They will not accept the electron generally because it is an electron precise molecule. They are normally not expected to act as electron acceptor or electron donor species. Although carbon cannot exceed its covalence more than 4, because the carbon has maximum 4 valency. Because carbon, how many? 6 electrons are there, 1s square, 2s square 2p2. Then outermost orbit, 2s square 2pt, 4 electron only can give, hence maximum 4 plus 4 is maximum. Inside 1s square it is not possible, it is very high, generally it is not seen till that. Then maximum covalency of carbon is plus 4. Carbon cannot exceed the covalency more than 4. Other elements of the group can do so. Why? Why they can show more than 4? Other heavy elements in the same group, then now it is very clear, because they have d orbitals. That electron also can be, they can donate, they can give, hence more than 4 valency is possible. F is also there in heavier elements, and they can give more than 4. Okay, but carbon maximum is 4. Other elements of the group can do so. It is because of the presence of d orbitals in them. Due to this, their halides undergo hydrolysis. Due to this reason, their halide undergo hydrolysis and have tendency to form complexes. Why? Because they will take the electron and it will go and it will give to, and this electron will go to the d orbitals. That's why they will make complexes. And in that, the covalency will be more than 4. Due to this, their halides undergo hydrolysis and have tendency to form complexes by accepting electron pairs from the donor species. For example, the species like SiF6 2-, SiF6 2-. Why 2-? Because fluorine, 6 fluorine is there, then 6 negative. Then silicon has 4 positive, then 4 positive, 4 negative. It is neutralized. Hence, finally, overall, 2 electron will be, 2 negative charge will be left out. Hence, SF6 2 negative. Like that way, other also, germanium GeCl6 2-. Same way, germanium plus 4 it is showing, and 6 negatives are there. 6 fluorine means 6 negative. Then 4 will neutralize, 2 negative will be remaining. That's why it will show 2-. Stannous also, SnOH whole 6, SnOH whole 6 2-. Again same way, OH has 1-, Sn has 4+, then 4+, 4- neutralized. 2 negative charge will be left out. That's why SnOH whole 6 2- exist, where the hybridization of the central atom is sp3d2. sp3d2, because 6 OH6, F6, Cl6 are there, then 6 means this hybridization should be 6 orbitals should be there. Then sp3d2, 1s means 6 orbital mixed up, 1s, 3p and 2d. Then 1 plus 3 plus 2, 6. And they are giving, after mixing After mixing these 6 orbitals, they will give 6 orbital, new 6 orbital, and their energy will be almost same, not 100%, almost same, and process is called hybridization. Means you can tell orbitals of equivalent energy. Orbitals of equivalent energy. After hybridization, you will get same number of orbitals, but in the before hybridization they will having different energy. But now after mixing and giving new orbitals, then their number will be the same, but energy will be almost equivalent, not 100% same. Now I am telling you next properties, that is the reactivity towards oxygen. All members when heated in oxygen form oxides. There are mainly two types of oxide. First one monoxide and second one dioxide, of formula MO and MO2. M is the metal, MO and MO2 respectively. SiO, see this is exception, exception I am telling you, SiO, silicon oxide, this is the monoxide. SiO only exists at high temperature. At high temperature, only SiO exists. Oxides in higher oxidation state, again important things. Oxides in higher oxidation state means +2, +4, like that way. Oxidation in higher oxides in higher oxidation states of elements are generally more acidic. By seeing only molecule, you can tell if more oxygen is there, then that will be acidic, because that will have more, you can say, this oxidation state. And this I told you in comparison to the lower oxidation state, higher oxidation state will be, you can say, more acidic. This is very important. Now the dioxides, example of dioxide of carbon dioxide, CO2, very gas, very common. Then this is the common dioxide. Okay, the dioxides are carbon dioxide, silicon oxide, SiO2, sand, sand is sand in building material, that is actually silicon oxide, SiO2. Third example, germanium oxide, GeO2. One oxygen means -2, then two oxygen means -4, then germanium will be +4, like that way SiO2, then two oxygen means -4, then Si will be +4. Carbon same way, two oxygen, CO2, two oxygen means -4, then carbon will be +4. Then these are acidic, these oxides are acidic. Question is asked. Okay, only from this reactivity towards oxygen, 4-5 things are there, that question is asked. Now again you can see, whereas SnO2 and lead oxides are amphoteric. Again question is asked. Okay, SnO2 means this stannous oxide, SnO2, stannous oxide and lead oxide, PbO2, are amphoteric. Amphoteric in nature means they have both properties, acidic as well as basic, amphoteric. Okay, among monoxide, carbon, CO is neutral. Again question is asked. Always this type of, only from this point many questions are asked. Then CO is neutral. Always remember CO is neutral. And GeO, germanium oxide, GeO is distinctly acidic. This is also acidic. GeO is acidic, whereas SnO and PbO are amphoteric. Okay, amphoteric. Now this question is also asked. Then SNO and PBO, lead oxide and stannous oxide are amphoteric. All full what I told you. Every point is important for examination. Okay, one marks question. Now another important things I am discussing problem that is asked in examination. Question is that select the members of group 14 that first forms the most acidic dioxide, second is commonly found in +2 oxidation state, and third used as semiconductor. These 5 members are there. Then out of 5 members of 14 group, actually 6 one, you know that is not found. Okay, vacant states are there. Then 5 are now common, it is found. Then question is asked that select the members of group 14 first forms the most acidic dioxide, second is commonly found in +2 oxidation state, and third used as semiconductor. Already I have told you. Now if you will think, you will get the answer also, but now I am telling you answer. Then first answer is carbon. Carbon forms the most acidic dioxide, CO2. I told you. Okay, CO2. Then carbon is the answer. Okay, first answer. Second is the question the commonly found in the +2 oxidation state. Then +2 oxidation state commonly found is lead, and third used as semiconductor. Then already told you silicon and germanium. Then this question is also, this type of question is also asked. Already it is a problem, I have told you this question was asked. Now I am telling you reactivity towards water. Carbon, silicon and germanium are not affected by water. This is also important question. Carbon, silicon, germanium are not affected by water. Okay, these questions are fit for medical and engineering. Now come to the tin. Tin decomposes steam. This is also important. What I am highlighting, you should note down or keep in mind. Question will be asked. Tin decomposes steam to form dioxide. Okay, means if steam is there, steam, you know that vapor means steam is denser than boiling water. Steam has more energy than boiling water. Then tin decomposes steam to form dioxide, means SnO2 it will form. Also it will give hydrogen gas, means Sn plus 2H2O. On heating it will give SnO2 plus 2H2. It decomposes steam, that is important things. Now lead is unaffected by water. Again important question. Lead is unaffected by water, probably because of a protective oxide film formation. Reason also I am telling you why lead is unaffected by water. What is the reason? That because of protective oxides film formation. Now I am going to tell next property, that is the reactivity towards halogen. These elements can form halides of formula MX2. M is metal, X is halogen, fluorine, chlorine, bromine, iodine. And also it forms MX4, MX2 and MX4, where X is equal to fluorine, chlorine, bromine, iodine, that is halogen, commonly known as halogen, collectively known as halogen. Except carbon, now exception we can see, except carbon, all other members react directly with halogen. Okay, carbon is in exception. Under suitable condition, except carbon, all will react with halogen. Most of the MX2 are covalent in nature. MX2 are covalent in nature. The central metal means M. Okay. I was talking most of the MX4 are covalent. MX4 metal tetra. Okay. MX4. If X may be Cl, Br, I, F, anything. Then most of the MX4 are covalent in nature. The central metal atom in these halides undergo sp3 hybridization. sp3, 1 S and 3 P, total 4. Then MX4. Then that is, it is sp3 hybridization, and the molecules is tetrahedral in shape. This question is also asked. In this two question, that is what type of, in MX4, what is the hybridization of metal ion, then it is the sp3 hybridization, and shape is tetrahedral. Exception you can say. Exceptions are also there. Exceptions are SnF4, stannous SnF4, and other is PbF4, lead tetrafluoride and stannous tetrafluoride are in exception, which are ionic in nature, because both are metal, that's why, that is the main reason, and others were non-metal. Then exceptions are SnF4 and PbF4, which are ionic in nature. PbI4 does not exist. Again, important question. PbI4, lead tetraiodide, does not exist. Why? Because PbIodine bond initially formed during the reaction does not release enough energy to unpair 6 electrons and excite one of them to higher orbital to have 4 unpaired electrons around lead atom. Because I told you that NS2 electrons that will not take part in reaction. Then in case of iodine also this happens. That first iodine is coming, then okay. But that time when they will come, it will release the energy. But that energy is not sufficient to remove this S electron. Then higher oxidation state they will not get. Then there will be no reaction. Okay, this is the main reason. That this I told you that 6 square, in this case electrons, this PbI, lead iodide bond initially formed. They will form lead iodide with one iodine. And PbI bond initially formed during the reaction does not release enough energy to unpair 6 S square electrons and excite one of them to higher orbitals to have 4 unpaired electrons around the lead atom. That's why PbI4 is not possible. Okay, this is the important things I have told you. Now heavier members as for example, germanium and lead are able to make halides of formula only MX2. G means they can form GeX2, PbX2 means Pb chloride, lead chloride, germanium chloride, like that they will make. Stability of dihalides increases down the group. Considering the thermal and chemical stability, if you will consider thermal and chemical stability, then germanium GeX4 is more stable than GeX2. Again important question. GeX4 is more stable than GeX2, and with lead it is a reverse case. GeX2 is more stable than GeX2, whereas lead X2 is more than lead X4. Reverse case. GeX2 is more stable, and here lead X2 is more stable than lead X2. Now, except carbon tetrachloride, other you can say chlorides are easily hydrolyzed. Carbon tetrachloride is an exception, CCl4. Except CCl4, other tetrachlorides are easily hydrolyzed by water. Because why they are hydrolyzing? Because the central atom can accommodate the lone pair of electrons from oxygen atom of water molecules in d orbitals. Okay, this is the main reason, because the central atom can accommodate the lone pair of electrons from oxygen. H2O means what? Oxygen is there, and oxygen has lone pair of electron. Then this you can say central atom can accommodate this lone pair of electrons from oxygen atom of water in d orbital. Now again I am telling you further, hydrolysis can be, if you want you can understand by example. Okay, silicon tetrachloride example I am giving you, then you can understand that SiCl4 plus H2O. Then H2O has two lone pair of electron. Oxygen has two lone pair of electron. Then what will happen here? Silicon will take these two electron. One pair of electron silicon will take, and it will form one OH will come, because H from the H2O, one H will react with HCl. With Cl, one H will react and it will form HCl, it will go out. Then now in that place lone pair will be accepted, because Si and Cl, two electron was involved. Then chlorine is taking the electron. That electron of silicon also it is taking and went and given to H plus. Then as HCl it is going outside. Then now in the place of that this lone pair of electron is going, two electron from the oxygen, because Cl went with both electron, its own electron plus silicon electron. The silicon become Si plus. Then they require two electron for the bond formation. Then oxygen, one lone pair of oxygen it will take, and HCl will go out and it will form OH will be attached there. In the place of Cl now OH will be attached. Then it will form Si3Cl and one OH. And again what will happen? Because OH is there, then now further if suppose more molecules of waters are there, more water is there, then same reaction will repeat. Same, because 3 Cls are there, then all 3 Cl will go, and in the place of Cl, OH minus will come. Replacement, because Cl is also electronegative. Cl has one negative, OH is also one negative, hence it can be, substitution can take place. Then all 3 will go out, means 3 HCl, means 4 molecules of HCl is there. Then from all 4 molecules of HCl, one H will come. As HCl it will go, 4 HCl and 4 OH will come. Hence it will form silicic acid, SILICIC, silicic acid. From the silicon, the word silicic has come. Silicic acid, SiOH, 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 means SiOH whole 4. This is the silicic acid. Again, in the end, I am telling you one problem. This is the last. Okay. Then question is asked. Problem is there. I am reading the problem. SiF6 2 minus is known. SiF6 2 minus is known, whereas SiCl6 2 minus is not known. Why? This question is asked. Question is not, it is asked. Already problem is there. This question is already asked. SiF6 2 minus is known, whereas SiCl6 fluoride compound is there. SiF6, but SiCl chloride compound is not there. Why? Does not exist. Why? Give explanation. This is the problem. Now I am telling the solution. There are two main reasons. First, 6 large chloride. See, fluoride ion is a small. Fluoride is a small. Fluoride ion F minus is a small. But Cl, chlorine is big ion. Big ion. Then 6 large chloride ions cannot be accommodated around silicon because chloride ions are big. Then all 6 can't accommodate around the silicon due to limitation of its size. Silicon is small and carbon is big size. How they will accommodate? But fluorine was small, that's why accommodated. Then this is the first reason. Second, interaction between lone pair of chloride ions. Interaction between lone pair of chloride ions and silicon Si4 plus is not very strong. Again, Si4 plus is there, means they don't have electron. Already Si4 plus is there. Then interaction will be not there. Interaction between lone pair of chloride have how many lone pair of electron? Cl 3 pair of electrons are there, 7 electrons are there. Then 2, total 7 electron. Then it's chloride ion, when you are talking, then 3 pair of electrons are there. Then there will be, what will be 6 chloride ion will come, then 6, then 3 into 6, 18 pair electrons will be there. And silicon is there. They will come around this 6 will come near the silicon, and silicon is small. Then these electrons themselves will be repelled to each other. These 18 electrons will repel to each other. Hence bonding will be not strong. Okay. Interaction between lone pair of chloride ion and silicon is not very strong. That's why this SiCl6 2 minus is not existing. Okay. Now I am stopping only here. Next class I will discuss other term, other topic. Okay. Thank you.